Forces and free body diagrams. Now, up until now, we've been talking about velocities and accelerations and distances and times. That's one way of looking at the world. But now we can start to see the world as a constant pushing and pulling. In other words, we start talking about the forces that show up in the world. By the end of this lecture, I hope that you develop a concept of what forces are, identify that they are vectors, and introduce a way of representing them. Now, first vocabulary word is the term body, and most people think of, well, they occupy their body, but in physics, it's a generic name for any kind of object. And we can represent bodies by a geometric shape, for example, a circle or a box, and anything can be a body, from a book on a table to Michael Jordan flying through the air. Now, I don't have to draw Michael Jordan picture perfect. I can simply use a circle and call it Michael Jordan. The next vocabulary word is a force, and these are really integral for this idea of what's called Newtonian physics. And we're going to meet Newton in a minute here. But there's a couple key elements to forces. First off, they are a push or a pull. And just to be specific, a push is a type of force that moves something away from you. And a pull is a type of force that draws something towards you. Second is, a force is a vector, which means it has a magnitude and direction. And then finally, forces are measured in the units called newtons. Now, it's very common in science that if you do something great, they start naming things after you. And Newton definitely fits in this camp. In fact, Isaac Newton was a young student at Cambridge. And so here we go. As the story goes, young Newton was sitting underneath a tree in his college at Cambridge, which is a type of university in England. It's very prestigious, when an apple fell from a tree. Now, Newton wasn't the first person to see something fall, but Newton began to question, why is it that the apple falls towards the earth? Why isn't the apple something that falls away from the earth? And he started to develop some ideas of what's called gravity. And he found that apples behave very much the same way that the moon does, and in fact every one of the planets. And so NASA still today uses the ideas that Newton developed underneath that apple tree. He began to explore the forces, and he developed them into three famous laws that we use in physics. Let's look at them, at least the first two. Newton's first law deals with this idea of inertia. Now, Hewitt explains it this way, and I think it's pretty wordy, but I've tried to translate it into something that's a little more manageable. Why don't we put my sentence in your notes? Hewitt says every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero net force. Once again, that's rather complex, but I interpret that as a body will maintain a constant velocity until acted upon by an outside force. Now, this idea of constant velocity I put in bold for a reason, because an object at rest will stay at rest. An object in motion will stay in motion. That is what constant velocity means. Newton's second law deals with acceleration, and this is by far the most useful for this idea of free body diagrams. Hewitt says that the second law, the acceleration produced by a net force on an object, is directly proportional to the magnitude of the net force, and is inversely proportional to the mass of the object. Force net equals mass times acceleration. That is what this phrase means, or this sentence. And more importantly, F equals ma, which is a characteristic you will be using quite a bit in my class. So I want you to take a moment and look up and see if you can see a push or a pull. You know what? It's really hard to see the push or the pull. You can see the effects of pushes or pulls, and so you can see the effects of forces, but to point to a force by itself is pretty hard. So we use in order to represent forces, we use arrows to denote direction, and then the length of the arrow indicates magnitude. So for example, if I had a very small force, I will have an arrow, but it will be really short. If I have a big force, I'll have an arrow, but it will be longer. And in fact, you can see that this force is about twice as long as that force. Free body diagram is a picture of a body and arrows that represent all the forces acting upon that body. Now these can get pretty complex pretty quick. So, in order to keep things straight, I make an effort to color code my free body diagrams. Any information in the y-axis will be in blue, by the way that's up and downness, and any information in the x-axis will be in red, by the way that's left and rightness. So in my first example, I want to draw a free body diagram of a Newton's apple, and this is kind of a joke based after Newton. So if I have an apple and I'm holding it by a string here, are there forces acting upon this apple? I hope you were able to identify that, yeah, there is a force in this direction due to gravity. Force, gravity. The thing is, why is my hand here? What's that doing? Well, there's another force, and it is equal and opposite. It is the exact same length, but the direction is different, and this is force phi. So this is my hand is applying a force in the opposite direction. And so if I want to figure out what's called the net force, I add up all the forces going down plus all the forces going up. And so in this case, all the forces the force due to gravity in that direction is exactly the same as the force due to phi in this direction. And in essence, they cancel each other out, and you get a result of 0 newtons. Now, because I know that this is a Newton's apple, on the side of it, I am told that the force due to gravity is 1 Newton. But quick, which way is up? Which way is down? And since the arrow is pointing down towards the center of the Earth, I'm going to make this a negative number. Because I know that phi is supplying the exact same force, but in the opposite direction, I'm going to apply 1 Newton. And so if I look at my force net, I see that I have negative 1 Newton going down plus positive 1 Newton going up, telling me that my net force is 0 newtons. Out of interest, are there any forces going this way or this way? Nope. So I can say that the net force is 0 newtons going left and right, or in the x-axis. Well, my next example, I'm going to be looking at a book sitting on a table. And so this is my table. And so you might just represent it by a line, and then a square representing the book. Are there any forces acting on these books? Yeah, there's a force in this direction, and it's a force due to gravity. And I've found that that is 14 newtons. But it's negative because it's going in a down direction. Is there another push or a pull acting on this book? There is. The table is actually pushing up on the book as well. So the force table equals positive 14 newtons. And because it is not accelerating towards the center of the Earth, I can say negative 14 newtons plus 14 newtons, that's up, equals 0 newtons. In other words, the force due to gravity equals negative 14 newtons. The force of the table is positive 14 newtons, and they result in 0. Well, I've changed the scenario a little bit. What have I done? I've put an apple on top of my book. Now there's two forces. So not only do I have the force due to gravity of the book, which I know to be negative 14 newtons, I also have the force due to gravity of the apple, which is negative 1 newton. So here's my question. What's my force table now? Well, unless it starts accelerating towards the center of the Earth, my force table is now positive 15 newtons. In other words, I have the force due to gravity book plus the force due to gravity apple plus the force due to gravity, the force table. When I replace numbers for letters, I get negative 14, negative 1, plus 15. And when I do the math, I see that that equals 0 newtons.